Hi, my name is Eduardo Serna. I am a consultant at Wolfram Research. I work at the Probability in Statistics group with my colleague Kosa Konverska, who's also, we're giving this talk and the next one jointly. So she's around to, right now she's around to answer questions in chat and might jump in to mention, comment on something I might have forgotten, and I will do the same in the following talk. The topic of this talk, well, the title of this talk is spatial value, spatial estimation. But the topic of this talk is something that is traditionally known as kriging, and is something that this is the thing I started working on when I joined Wolfram like 5 years ago. I can't even remember. And this is the first thing that I did, and I gave a similar talk to this one in my first WTC, again, in 2015. So that's actually more than 6 years ago. And we in the end we didn't release that functionality back then. We came back to it recently, and I think we've come a long way. Although a lot of the implementation was there, but we've improved performance, and crucially we've improved design a lot. And I also hope, I was looking at my talk last from 2015, and I hope that this talk is also an improvement in that one. So to begin, let me just introduce what we're talking about. These are spatial data sets that consist of a set of measured values at specific locations. And they are becoming increasingly important with all of the the huge amount of data that we have access nowadays, spatial data. And the examples of this data are stuff like temperature, elevation, concentration of minerals, chemical compounds. There's a lot of data of this around. Even in 2015, there was a lot of interest in this already, and there's more and more interested, and we hope that this functionality is going to be useful to people, and I think we will. So I'm just going to preview upcoming Wolfram Language functionality in the next release. It's going to be experimental for now until we settle on a final design, but it's already come along well. And this functionality is to perform estimation of missing values or in a region of interest, the model and an underlying quantity. And as I said, this has many different names, but the main name it's been known for this procedure is called kriging. So let's start with an example to kind of understand what this functionality does. And let's look at a spatial data set of a continuous quantity that is measured at specific locations, and in particular with large gaps, which is where this functionality shines a lot. And in this data set that we're going to look at to begin with, it's our ozone readings over the contiguous United States. So I have the data here, and I visualize it with point value plot to show that there are indeed these large bands here where presumably the satellite that was taking these measurements couldn't. And spatial estimate is a very powerful estimator that is going to combine both large-scale trends and local variation to be able to fill in these gaps in a way that makes sense, but also give good results close to the data points that we've measured. So to begin with, let's create a spatial estimator function with a quadratic trend that measures the large scale variation. And we do this by just giving the data, the locations and the values, and we specify as an option the spatial trend function, and the argument is 2, which means that the order of the polynomial is of order 2, i.e. quadratic. So let's evaluate. We can just evaluate this spatial predictor function at uniform random locations in the region of interest, and we can see that and visualize it with point value plot to compare to the previous to the raw data we saw, and we can see that indeed it's doing a very good job of filling in the missing values in a way that makes sense, that it captures reasonably what we would expect to have in the gaps. We can also, for instance, just find the estimated value for a particular location, i.e. Boston, for instance. Okay, so this is the first example. Let's look at what the model looks like. But first, before looking at the actual model, I want to introduce as a warm-up or reintroduce a model that's familiar to a lot of us, which is ordinary least squares, to make a bridge to what we're going to be doing here. In ordinary least squares, we usually have like a set of locations, the xi, and a quantity of interest, which is the y values, and we're trying to model this with an m function that we're trying to parametrically estimate usually. And there's some noise, this delta variable, that is usually a random variable, Gaussian. It is, although that's not crucial, but it's usually Gaussian. It's independently and identically distributed with 0 mean. And once we've estimated it, once we have an estimate for this f function, which is called f hat, we can infer the value of the quantity y at a location not that we choose, just by evaluating f at that location. And we've had this functionality for a long time in Mathematica. It's called linear model fit, and we can let's look at a 1D example, which makes it easier to see what I'm trying to the points I'm trying to make. We have some data that clearly comes up and down with some noise. We fit it because it's kind of coming up and down. I'm going to fit a cubic model to it. So we have like constant, linear term, a quadratic term, a cubic term, and we get this fitted model that we can plot, and we see that this is like a reasonable estimator for this data. In this case, with spatial estimates, the model is very similar to that of least squares, generalized least squares, not quite ordinary least squares. So we still have a trend and we have a random component. But instead of using the estimated trend as the estimator, we're going to use a linear combination of the values, the measured values, with some weights that depend on the point at which we're going to be estimating. Some weights depend on our point of interest, and they are chosen to minimize this quantity, the expected value of the difference between our estimator and the underlying quantity of interest, the square, the difference of the square. And this makes it an unbiased minimum variance, because it's minimizing this quantity, linear estimator. So if we look at the previous example and we compute the spatial estimate, and now we plot it against with the data, the previous linear fitted model that we had, and now a spatial estimated function, we see that here we're capturing a lot of more a lot more of the features of the data set with this estimator, with this model. And in particular, this goes, we can see that it goes through all the data points, although this is not necessarily always the case or a requirement. Okay. So let's look at now, start looking at the random parts of the model. So we have a random component, which is a zero mean random component. And in this case, we split it up into a correlated component. That is a component that has a covariance, a correlation between different locations, and a white noise IID component, like essentially Gaussian. Again, and this model, and let's look first at the noise component, which, because the variance of this component, which we specify by the option spatial noise level, is a measure of how noisy the data is. And because this is an uncorrelated random component, and it's a measure of how noisy the data is, or in other words, how much our estimator should smooth things out, because the noise of the data, that means that we are less sure of the position of how what the estimator should be doing, and we should work less hard to go through all the data points. And we can see this by computing different estimators with different values of the spatial noise level. So this has noise. The variance of this model, this epsilon component is zero. That it is zero, and but we also have another one here which has like a relatively small noise level, and one that is a little bit bigger. And if we look at the plots, we see that the larger the noise level, the closer it is to the trend, or the less it works less hard to just go through all the data points. And this is a way to control smoothing. And only when we have spatial noise level goes to zero is the spatial estimate become an exact interpolator. By default, we make different choices, but by default, as we saw earlier, we choose something that is usually close to zero, but we try to avoid conditioning problems as we're solving a linear system. Okay. So going back to the trend part of the model, the trend part, much like in linear fits and model, this is linear model fit. It's estimated according to generalized least squares, and a feature of this estimator is that when spatial noise level gets very large, the estimator in fact becomes the least squares estimator. And I just want to show this here by showing two spatial estimator functions with a large noise level, and we've computed with a trend function. This is a cubic in this case and a quadratic in this case, and we see that indeed for the cubic case we have the same result. I'm plotting the cubic, the square, the least square fit that I had earlier, and the difference between the cubic and the least square fit. And actually, I can't really see the cubic here because they're the same line, but I can see the difference is zero. It's on the axis. If we have like a different trend, say a square, then well, the trend is something else. In this case, a cubic is a better fit to the data, as it usually is when you have more parameters. Okay. So the remaining part of our model, perhaps the more interested, although that's arguable, is specified by the eta is specified by a variable, and this is a random component that has correlation between the different points. And we specify it by a variogram, which is a measure of the expected squared difference between 2 points. And for a stationary random process, this is only a function of the distance. So let's see how this estimate, like how this different variograms affect the estimator by looking at an example, this time in 2D. So let's look at some data of some rainfall samples in Switzerland. As you can see, this is a pretty sparse data set with some locations and the values here indicated by different colors. Red is more. And let's compute a spatial estimator by fitting the spatial point data to spatial estimate, and we can use the key of the annotation, in this case rainfall, to specify the values that we're interested in. And if we don't specify the variogram ourselves, the spatial estimate will estimate a variogram automatically. In this case, it's fitting a cubic variogram, and we can have a look at what the estimated variogram function by querying it here to the estimated function, and we see that we fitted a cubic model with the following parameters and the following spatial noise level, which is also estimated automatically. And by looking at this plot, this is a plot of the variogram function, which is this curve here. The data points here is the empirical variogram, and this dashed orange line is the spatial noise level that we fit. These data points above are the binned variogram, the empirical variogram, and we also have a function to compute it separately. But you can see that they're essentially the same here. And as I was saying, by default, a suitable model is chosen, but we can also specify a variogram model ourselves to fit with a function estimated variogram model. So again, we specify the data, the values that we want, and we could fit, say, a linear model here. And we can see that the fit is worse, not just, I mean, it's not very surprising, but it could also be a reasonable fit, not just because we could see that this thing could have a wiggle, but we can compute the weighted sum of residuals, and we see that the sum of residuals is quite much higher for the linear variogram. And with this estimated variogram model, we can fit it in as a, we can feed it as an option, the variogram function option, to spatial estimate. And here we can see that the estimator for the better fit captures more detail. So this is the cubic, and we can see there's just like more detail in the fit, in the spatial estimate, compared to the linear variable. So it does have an effect, but we try hard. A lot of the work we've done recently of this function is just to automate. The first version, all of this you had to supply it yourself, and we automated all of this process out, so that if the user wants to if the estimate, if the, I don't know which, anyway, If the user wants to tweak the knobs, they can, but hopefully we provide very good defaults. And the reason we can't just plug in any model is because someone's saying something. I'm gonna reply to I'm guessing Gosset's also. There's this question. Says I'll reply when I'm finished. Okay, I'm sorry. So these models, the reason we can't just plug any function as a variogram is that these models must have a property that amounts to the covariance function of the different points. It has to be positive definite, as a covariant function must be the matrix of points. And so we provide a big family of models to choose from, all the usual suspects here. And I hope that people can see this. I checked and they could. Let me make it bigger. This is one of our documentation. And we see that we have like a big family of models with, you'll have different formulas, different shapes. And, by default, we choose something that could work with different data and choose the best fit. Okay. All right. So let me continue a bit. Another convenient thing of having a model is that it allows us to compute an estimate of the error. And you can do this by just querying some points and then specifying a second argument to use around, for instance, and it will give you a list of rounds. There are other, you can just ask for the standard deviation, you can just ask the value is the default, you can use round, you can you use lists. It's all vectorized if needed. And as an example, you can use this to give like, let's hope I can make this big. Okay. Yeah, like, I don't know if you can see it very well here, but I have like two transparent surfaces above and beyond the actual estimation surface. That is the actual standard deviation of the estimator here. So this gives you allows you to have some control, some idea of the possible error your estimator can have, assuming that the assumptions are met. But of course, you can always check that the variable makes sense. They have a good fit, all that. Okay, and just to finish, spatial estimates needs to solve linear systems, and the order that are the order of the size of the data sets. And this is an operation that has an algorithmic complexity that is cubic. And, this very quickly for moderately large data sets, it becomes infeasible. So, for instance, here we have like a data set that is 10,000 points. And if we try to solve the data point with all the points, this is going to be take very long. Partly because it's doing geo computations, or geodistance computations are expensive. Even though we have like we're using a faster algorithm that is not exact to it, that it doesn't have 16 decimal places, but almost, and it's much faster than the geodistance, the full geodistance that we have in the system, that is more precise but much slower. But also a lot of the time here, just solving this relatively large linear system. So for large data sets, by default, we're solving a local system, and the cost of the computation becomes linear in the size of the data. And this means that you're just really limited by the amount right now by the fact that it fits in memory. So here the computation is very, it's essentially instant, and then they're computing these data points. They're computing the estimation on a set of target points is just linear on the size of those target points. Okay, and this is the end of the talk. This functionality is going to be in the upcoming release. We hope it's going to be useful to people, and we're very interested in. This is not our field. I mean, we're working for the statistics, but we're not professional practitioners, and we've read a lot and we try to figure out what people wanted and what was useful to people. But if you guys take it for a spin and gave us feedback, it's super welcome. Let me see the questions. Okay, so Mads asked, so spatial noise level means interpolating only. Gosha has asked this. Yes, in the sense that the resulting estimated function goes to the data point. Okay. So yes. Okay, there are no files available. I'm gonna upload them as now. I was fixing typos until right before the talk. Yes. Okay. So spatial estimate, the annotations, because I'm sure knows, exactly, like it tries the first one, but you can specify the one you want. And for rain estimate data, points rain is used as input. If the spatial data contains observations too, can this also be incorporated into spatial estimate? Well, this is something that is tradition. If you want to do both at the same time, the answer is no for now. This is something that's called co-kriging, where you're krigging two variables at once, and this is something that we don't have there yet. So you have to do either rain or elevations now. But again, depending on how much interest there is for it, we might implement it again. Yeah.
Thanks, Eduardo. Yeah, I think that's all the questions for now. I know you have another meeting right away after this one,
Okay.
so I'll let you
Yes.
go. If anybody has more questions, they can contact you or Gosha. Do you guys have office hours? I forget.
Like, you mean the WTC? Yeah, we have like an office
Yeah.
hour slot. Yes, that will
Yeah,
be
like
there.
they can put a chat in the
Yeah,
group
yeah.
office hours
Yeah.
and whatever, and they can contact you through Pathable directly. So if anybody
Yeah.
has more questions, do that. Eduardo's got to go to his next talk.
Yes.
Thanks
Yes.
again,
All right.
Eduardo.
Thanks so much. Bye, guys.